What's up, scholars? Today I'm going to be running through the solutions for the practice quiz. It's not an AP question from the AP, it's one that I have written that models an AP question fairly closely. So we're going to go through it together, and this is going to help you think like I think about a problem like this. We'll do some annotating, much like we have in the past, and we'll talk about which parts could be tricky for you. So we will start by carefully reading the question and annotating that as we go along. I'm probably going to get stopped right away and jot down equations. Let's jump right in. So it says a cannon with a mass of 1,200 kilograms. Ooh, let's label that M1. M1, 1,200 kilograms. Fires a projectile with mass, M2, with mass 4.0 kilograms. The average force, let's call that F, generated by the explosive gunpowder applied for 6.35 milliseconds. Ooh, that looks like that's going to be a delta T. So that's 6.3 times 10 to the minus 3 seconds is, so this is the force. This force is 255,000 newtons, 255,000 newtons. After leaving the barrel, the 4-kilogram projectile collides with a smaller train car with mass of 300 kilograms. Now we get to make a choice here. It's just as easy to call that M3. Why not? So it's going to bump into another train car. The projectile embeds itself into the side of the train car, and both objects slide together in the final speed. So it sounds like we've got, well, I've got force and time. That sounds like it's going to be an impulse question. And then we've got the projectile smashing into the second train car or another object, hitting it and sticking and sliding together. So that sounds like a collision. So right away I'm thinking we're going to have a impulse and a collision. So this is kind of two questions in one. Let's go into the first question. It says, draw a picture of the scenario with an appropriate symbols, label all masses, velocities, any other relevant data. Also, write the equations for momentum, conservation of momentum, and impulse. Ooh, so I was kind of on the right track. We're going to need momentum, conservation of momentum, and impulse. Now, scholars, I'm going to let you in on a little secret. Almost never are the AP going to ask you to do this, but I think this is really helpful for making sure you understand the scope of the problem. The other thing that I think this helps you do is you have to hold less stuff in your brain, fewer mental gymnastics. You're not juggling all this information, it's just on the paper. So I'm going to work on drawing this. I'm going to pause the video for a moment. You do the same. Draw a cannon launching a projectile, and then later it's going to smash into a third object, a little train car. So I'm going to draw that picture now. So I'm going to let you in here in the middle. I've got my very poorly drawn cannon, the big wheel there. It's got M1 of 1,200 kilograms, and it's going to have an initial velocity of 0 meters per second. I've got my, this is kind of after the thing is launched, so I've got my second mass 2, that's the cannonball or the projectile, that's 4 kilograms, and before the actual launch it had a, so V2 naught is going to be 0. It has no initial velocity. You have to imagine the cannonball sitting inside of the cannon, both of them at rest, and then the charge is fired. The cannon is launched. So I'm going to label kind of over here that the force applied by the cannon, or the gunpowder in the cannon, was that number, 255,000 newtons, and that happened over a time of, what is it right here? So 6.35 times 10 to the minus 3. 6.35 times 10 to the minus 3 seconds. Now, I don't trust myself. We need to move that, how many? 3 places to the left, because you got 10 to the minus 3. So that's going to be, delta T is, so move this over 1, 2, 3. So there's 2 zeros to the left, 0.00635. So I don't trust myself when it comes to, to doing powers of 10 there. So I double checked. I'm going 3 decimals, 1, 2, 3 to the left, and now I've got it in seconds. We do, when we do calculations, need to be in standard units. We can't use milliseconds or this. I mean, you could plug this in, I suppose. But anyway, we've got force and time in standard units. Let's keep drawing the rest of this. So this is going to launch It's going to go through the air. We're going to assume it travels in a straight line, doesn't lose any energy or things like that. So now we've got this is going to be our cannonball again. So M2 is going to collide into a train car, which I have poorly drawn. We'll call that M3. This is going to have some unknown velocity that we don't know. Let's assume that it's going straight sideways. Just for sake of this problem, it's going to be a one-dimensional problem. And then we're going to say V3 initial is going to be 0. After they collide, it's going to have some unknown velocity. So V2, it's going to be the same velocity as at the end of this. V2 initial in this problem, it's not going to be 0. It's going to be some unknown value that we're going to determine later, I believe. And then we need to find their V as they travel off together, the final velocity of the two of them stuck together. Ooh, my head got in the way. So this is the kind of picture that we want to be able to draw. We've got a launch, and then we've got a hit and stick. I think that's good. Oh, we need to write down our equations. So we need momentum. That's P equals mv. I want to remind myself that those are both vectors. Conservation of momentum, that's m1 v1 naught plus m2 v2 naught equals m1 v1 final plus m2 v2 final. Now keep in mind that once we get to this collision, we can change up those numbers. This just represents the momentum before the collision on the left-hand side of whatever two objects. So it could be these two objects or these two objects, and then this side represents their momentum after the fact. Finally, I want to write my impulse equation. That's delta P equals F delta T. So we were almost 7 minutes into the video. We've done a lot here to set this up, but this is going to make everything go much, much faster now that we have all this information written down. Now the first question says, determine the muzzle velocity of the projectile as it leaves the cannon. Now, velocity, that's going to make us think probably that it's going to be the momentum equation, because you got V sitting right there, or maybe it's going to be conservation of momentum. The trick is that we know the force, and we know the time, and it's just asking about the muzzle velocity of the projectile, which actually makes me think that we're going to use the impulse equation, because the impulse equation is a little bit sneaky. Let me show you what I mean. It's delta P is F delta T. The change in momentum of that projectile, the 4 kilogram projectile, is going to be the force applied to it times the time it's applied for. So we can actually expand out this left-hand side. It's going to be delta mv is that same thing. So we want to know the change in momentum of the cannonball, where we're just talking about one object. So a hint, and I know I've said this in class, but a hint is that when you have delta P, or when you have the impulse equation, this is for one object only. We only have the force applied on the projectile here. So let's expand this left side out even a little bit further. It's going to be the change in momentum. Oops, so that's going to be m, let's call it m, what did we say? It's going to be m2 v final, because this is going to be the, when you do change, you do final minus initial, minus m2 v initial. Now the nice thing for us is that the cannonball was sitting inside the cannon, not moving, so this term is 0, and that equals F delta T. Now if we look at this, we've got, I'll just rewrite this, m2 v2, or v final, so that's the mass of the cannonball times its final velocity, which we do not yet know, times the force times delta T. So actually we know everything in this equation except for that final velocity. We'll solve for final velocity. I'll just divide both sides by m2. So v final is F delta T over m2. I'm going to take a moment to plug that in my calculator. So I've plugged in the force in newtons, the time in seconds, the mass of the projectile in kilograms. It's got that here in my calculator. I'm going to hit enter. So 404 meters per second. That is really fast. We'll round that to 405. Now that's somewhere close to, a little bit higher than the speed of sound, but it's not like completely way too low or way too high. Again, I made this question up, so it seems like a reasonable answer to me. Then it says calculate the momentum as a projectile leaves the cannon. I've told you before that this is a pretty unusual thing. Almost never will we actually want to know the momentum. But that's really easy. Momentum is just P equals mv. So it'll be 4.0 kilograms times 405 meters per second. Now, to deal with the vector here, we'll say that this is a positive velocity. It's moving off to the right-hand side. We can plug that into our calculator. 405 times 4 is 1620, and that's kilograms meters per second. And I'm going to say to the right. That is the momentum of our cannonball. 1620 kilograms meters per second to the right. Remember, this is the kind of dumb unit for momentum. Now, I like D, and I think this is going to be a helpful thing to think about, especially in terms of bringing some concepts together. But the question reads, without additional calculation, what will be the momentum of the cannon after the projectile leaves the cannon? Explain your answer. Now, this is a collision. We kind of are mixing impulse and collisions. If momentum is conserved, the initial momentum of this system, they're both sitting still, is 0. And the projectile leaves with this amount of momentum to the right, then the momentum of the cannon has to be, we'll put momentum of the cannon, has to be negative 1620 kilogram meters per second. Now, by putting negative, I've implied that it's to the left, so I don't need to write to the left again. But I will put that in parentheses. This is to the left. Now, I don't want to put it like I did here, negative, and then to the left, it's sort of like a double negative, so I'm just going to put this answer in a box. But you can imagine, and maybe you've seen videos of this before, of a cannonball being launched one direction, the cannon being launched or recoiling in the other direction. That's what's going on here. It's a conservation of momentum kind of situation. Let's move to the back side. So this says calculate the recoil velocity of the cannon after the projectile leaves the barrel. So this isn't too bad. We know the momentum equation. This will be for the cannon. It's mv. We know this number is negative 1620 kilograms meters per second. We know that the mass of the cannon was 1200 kilograms. So if you plug in 1200 and we have the V final of the cannon, then we can solve it for that. So it'll be V final would be divide both sides by 1200 kilograms, negative 1620 rather, kilograms meters per second, divide by 1200, and we get negative 1.35 meters per second. Now, we can do a quick gut check. Does that answer make sense? Well, it came out negative, which is what we'd expect. The cannon's going to be moving backwards. 1.35 meters per second is like a little bit faster than walking speed, which tracks. If our projectile is being launched wicked fast off to go crash into something, it's pretty light. It was only 4 kilograms. So something with the same momentum in the opposite direction, it's much, much heavier, 1,200 kilograms heavier, or 1,200 kilograms rather. It makes sense that it would move slowly and in the opposite direction. So we can always do a quick gut check to see if that makes sense. And then let's move on to the last question. It says, assume the projectile loses no kinetic energy or momentum while it travels from the cannon. So I kind of mentioned that earlier. We kind of have to assume this is all a 1D ideal kind of situation just because we're not equipped to do much more than that. While it travels from the cannon until the projectile hits the small train car. Determine the mutual velocity of the projectile and the train car as they travel off together. So we can kind of ignore the beginning of the question. It's over here, beginning. All we care about is that the cannonball is flying with, what did we say it was? 405 meters per second to the right. So we'll call this M2, that's 4 kilograms. It's got an initial velocity, let's call that V2 naught in this case. It's going to be off to the right, and that's going to be 400 and, what did we say? 5. Very forgetful this morning. it's going to bump into a train car, or again, our poorly drawn train car that has a mass of, what did we say it was? I thought it was 300. Yeah, 300 kilograms. So we'll call that M3, 300 kilograms, and its initial velocity was 0 meters per second. Now they're going to hit and stick together. We're going to say this is after the crash. They are going to, I'm going to draw a poorly drawn thing here. So this mass is going to be the two of them added together, which is going to be 304 kilograms. We want to know their mutual velocity after the fact. So this is a classic kind of collision question, and so we'll set that up right here. So we're going to use our classic conservation of momentum. Here we'll go m2 v2 naught plus m3 v3 naught equals m2 v2 final plus m3 v3 final. So same conservation of momentum equation. We can put whatever subscript we'd like. The nice thing when we use this is we can do lots of rearranging and canceling. We're almost never going to plug in all four. Here's what I mean. The cart was sitting still. The train car was sitting still at the start. So this is going to be 0. V3, 0 was 0. So that whole term goes away. And then if we look here, they're going to be stuck together. So their masses are going to be a mutual mass. Their velocity will be a mutual velocity. So we'll call this just maybe m. Now, why don't we call that m2 plus m3? That'll be their mutual mass added together, which we already said it was 304 kilograms, times that final velocity that we do not yet know. And this will be the details of the projectile from the early part of the problem. So m2 v2 naught. Now, if we take a quick look and look at what we know and what we don't know, we actually know everything that we need to know to solve this. We know the initial velocity and the mass of the projectile. We actually know this number because we knew the momentum. I'm not going to use that. But we do know this whole side. We do know those two masses. We can solve for V final. So I'm going to do that. I'm going to divide both sides by this term, M2 plus M3. So we'll have V final is M2 V2 naught over the two masses added together. And we get this. So let me go ahead and plug everything in, and we'll get a final answer. We'll see if it makes some modicum of sense. All right, so I plugged in the information on the top. That's the momentum of the cannonball from before. So you could have plugged in, this is 1620 kilograms meters per second. We already knew that number, this stuff right here. But I just decided to plug it in from scratch. And then we're going to divide by the mutual mass of the two stuck together. You can see I've got that plugged in to my calculator there. So we'll hit enter, and we get 5.3 rounded, 5.3 meters per second V final. Now, let's do a quick gut check. Does that number make sense? This object is in between the masses of the lone projectile and the big cannon, and this speed is in between those two numbers, between the huge 405 meters per second and the very small negative 1.35 meters per second that the cannon went with backwards. So I'm pretty comfortable that that number makes sense, and it would be like a sled of the two of them moving off to the right. So that was a long way to go to get through a whole free response question. Took me about 20 minutes, which is approximately how long it should take you on a quiz or a test when you see a question of this length and of this difficulty. Now, to be clear, there's really no tricks in a question like this. I mentioned in the original description, this is really sort of like a standard, high school physics question that involves collisions and momentum, with no real tricks thrown into it, except for that it is a long problem with lots of details. So this is the kind of question that you should feel reasonably comfortable with, and I went through it in lots and lots of detail for you. So thank you for watching, scholars. Good luck out there.